So, now we will start with the, so we have seen 6-membered ring system and then 5-member ring system. Now, we will see the 4-membered ring system. Cyclobutanone. Okay. This on photolysis, this is not like a cyclohexanone or cyclopentanone system. Most of this the photochemistry of cyclobutanone is predominated from the singlet state. Okay. It never undergoes any inter-system crossing to the triplet. Most of this case you will see that the photochemistry is happening from the singlet, but it is n pi star, but from the singlet n pi star actually. After this it can undergo an alpha cleavage. Be an acyl and alkyl radical. Most of the your primary photo process ends up in a acyl and alkyl radical. It is only about you have to know which from which state the chemistry happens. Except cyclobutane, most of the chemistry happens from your triplet. Okay. Now, we will see that what are the secondary process it can do. It has some interesting secondary process like we can think about. First thing you can think about your decarbonylation. So, decarbonylation giving you get a 1,3 diradical system. So, we have seen 1,5 diradical system, we have observed 1,4 diradical. Okay. Now, we are seeing 1,3 diradical. So, what this 1,3 diradical does? What products I can expect from 1,3 diradical? Same way you can have your cyclization to give me cyclopropane type of system. Right. And then you can think about your same like your 1,5 diradical, you can think about your hydrogen abstraction. Get systems like this. Okay. So, this what 1,3 diradical does, fine. Okay. Any idea what this molecule, any secondary process it can do? Anything interesting secondary process which this particular radical can do? Type of 1,4 diradical, it is type of 1,4 diradical, right? 1, 2, 3, 4, 1,4 diradical. 1,4 diradical we have studied. It can do beta cleavage. So, if it does beta cleavage, then what you are ending up? You will end up with your ketene, right? You can end up with ketene plus you can end up with your So, it looks like more like a 1,4 diradical system doing its beta cleavage. Another interesting thing this does is ring expansion. This is beta cleavage. This is ring expansion. Can take this radical, okay. See what happens, ring expansion. What you are thinking of? Any idea what you can get? It's a radical, okay. You get a nice product. Can you write that? What do you get? You get oxacarbene. So, this is a unique of your cyclobutadiene type of system. You get in several example you can see you are getting oxacarbene system. Oxacarbene is formed in most of the cases, and if it is done in the presence of methanol, then because it is a carbon, right. So, you can write your, so you end up with this product. Which one?
Can this carbon add to a double bond?
Yeah, it depends upon in what system you are doing. Yeah, if you are, because after this it is carbon reaction. Okay. So, it depends upon the environment, what environment. If you want to trap that carbon, you can trap that carbon, whatever. But normally if you do the photolysis in methanol, then you get this product. Okay. See, this is very interesting, is you get decarbonylation, that sometimes dominates. See, all these three reactions dominates most of the time. See, decarbonation, it's allowed because the cyclobutane, it wants to break it up, okay, so that the ring strain is overcome. So, that is dominating. Then you are saying that, sir, I get 1,4 diradical, then beta cleavage is also dominating reaction, and this ring expansion, because the driving force for the ring expansion is the formation of your carbene. So, that also dominates. So, these three reactions dominate. Okay. So, that is why when you do in solution, you have to understand like what product we are looking for, or you are doing in methanol, then you most of the time end up with the carbene, oxacarbene reactions. Beta gamma
unsaturated carbon by abstracting the intermolecular hydrogen.
By abstracting which hydrogen? The beta hydrogen. Oh, you want to do that intramolecular hydrogen abstraction. Yeah, that can also abstract, but these are the three dominant products you can see. That might be the minor products. Okay. So, that is why like cleavage reactions are interesting, because like you study more about radical chemistry in cleavage reactions. Like first you taken a saturated cyclic system, a saturated acyclic system, and you studied all about the chemistry, right. Then you took a 6-membered, you tried to study 1,5 diradical system, then you took like cyclopentanone 1,4 diradical. Now you are taking a cyclobutadiene system, trying to understand 1,3 diradicals. So, it goes like that. So, we will see in the same class how we can involve the double bond into these radicals. That will be really interesting. Okay. If I do my photolysis, I get to my S1, okay. From there I get my alpha cleavage. So, which side you want to break now? You have two options, you can cleave here or you can cleave here. we you can cleave B, because again you are thinking about a secondary radicals. Okay. If I cleave A, I will be getting my primary radical CH2 dot. Here it will be CH with an ethyl. So, I get this product now. I can do my decarbonylation. See, decarbonylation happens very fast because it's a cyclobutane at the end of the day. So, you will get ethyl dot and you will get your OMe with this. And you get a type of, see, this type of ring system, forming this type of ring system is possible most of the time by your photochemistry. Okay. Cyclopropane type of systems that can happen. And then you can do your ring expansion, you can try your ring expansion by yourself and see what product you are write by yourself, ring expansion. And in methanol what happens? Anyone can tell me what carbon it is, whether it is a singlet carbon or triplet carbon. If it is singlet carbon, okay. How you know it is singlet carbon?
Because that oxygen won't be a donation to that vacant below.
They can be also triplet. Nah? From what is difference between a singlet carbon and how you differentiate a singlet carbon and triplet carbon? Any idea? Yeah, how you differentiate? Yeah, whatever you said just right. How you can differentiate them? I ask you, I give you a singlet and triplet carbon, I give you some reaction, I tell you by the reaction differentiate me that this is singlet carbon and this is triplet carbon. How you do that? Okay, I will give you a clue. I give you an alkene.
Triplet carbon can add to a double bond.
Singlet also adds to a double bond. Singlet carbon?
Singlet carbon gives double product, but triplet carbon you get only a single product.
Is it the other way around?
Rotation takes place.
Is it the other way around? Singlet carbon gives you one stereospecific product, right? Triplet may you get as a two products, because in singlet carbon the reaction is concerted, but triplet carbon the reaction is radical. So, it goes step by step. First and it attaches to an alkene, then the bond rotation can happen place, then it can form. So, you can get many stereo products, okay. But singlet reactions are very stereo specific. Clear? So, how we know then this reaction is stereo specific? We can take examples where you have a chiral thing and then we can see whether what carbon we are getting, okay. Are we getting H, O, E, M, E in different directions? Do not worry, I will work that example. That time I will ask you what is the major product. Same cyclobutanon system, we can take a very cyclobutanon system where you can take chiral centers and this, and we can treat them whether it is a singular carbon or not. So, I am taking a cyclobutanone, okay, and I am taking an alkene molecule, and I said that yes, I will do a photolysis, normal photolysis. Okay. So, I take cyclobutanone, add some alkene of this and carry out my photolysis. What you can expect? So, as you said, first it goes to singlet, that is fine, then get to singlet, then you know that it undergoes an alpha cleavage. So, I will take this alpha cleavage product. See, now it does not do any decarbonylation, all these things, because it has an alkene to it. Let's try to react with this alkene, right. So, your acyl radical can add to your CH2, giving me I get this. Yes, right. Then so, I get 3 vinyl cyclohexanone. 3 vinyl cyclohexanone. See, this is a very good experiment, because I can say that I have trapped my 1,4 diradical. This is a best example for trapping. Okay. If someone asks like, are you sure that you are getting 1,4 diradical? Okay, this is very good example. You take a cyclobutanone, add your alkene and you photolyze, you end up with your vinyl cyclohexanone, 3-methyl vinyl cyclohexanone, right. Very good trapping experiment. Now, so that is more about your systems like cyclic systems, where I have taken 6, 5, 4. We discussed about this 3 ring system. Initially, we started with an, see what 3 ketones we said, which you can observe this Norrish type 1 reaction. One, we said it should be a saturated acyclic system, or it should be a saturated cyclic system. So, acyclic system we took 3 examples. One, we took symmetrical ketone, okay, and then in other side we took a ketone where both the arms of the ketones are different, okay. Then we took an example where the ketone as a beta hydrogen, okay. So, we did 3 examples on acyclic system. Then we came to the saturated cyclic system, where we took 6-member ring, 5-member ring and 4-member ring. So, one more we have to discuss, that is your beta gamma unsaturated ketones. Okay. If you have a ketone where is unsaturated is within the ring, then what type of chemistry it can do? See, for example, I am saying beta gamma. We will discuss other unsaturated also. Okay, but first we will start with beta gamma unsaturated. We will take a system where type of cyclobutanone 4-member ring system, not cyclobutanone. We will take a 4-member ring system. Okay, we will take this system. Now, what happens? You know, you have studied about cyclobutanone, like 4-member ring system with a ketone, but now what I am doing is that I am slowly introducing a concept of double bond here. Okay. So, now I am saying, like if you say alpha beta gamma, so you have a double bond in beta gamma. In that case, what this 1,4-diacyl radicals can do, 1,4-diacyl radicals, whether they can involve the double bond into the system and do the chemistry something like that, or they leave the double bond isolated, that we can see. So, you know that this undergoes a photolysis, mostly it takes from S1, get an alpha cleavage. I can think of 2 products here, right? Both the sides it can cleave. We call this A or B, which will be better? B is good, right? You want to generate an alkoxy radical. If I cleave on the A, you will be generating an alkoxy radical, which is not like very hard to make. But if you think about B, I will be generating a tertiary type of radical system, which is like stable. So, I will get a product then. We get a system like this. What this does, this is your primary process, right? Up to this it is a primary process. Now, we will see what this radical does in secondary process. This can do now what? Because it is a again a 1,4-di radical type of system, right, which we have studied. So, what it can think about doing? What we have studied 1,4-di this type of cyclobutanone system. What are the secondary process? One is you have seen any recombination in 1,4? No, there is no recombination happens. Then no, then you are thinking about beta cleavage. That is very hard in this system. Again, you are trying to generate an alkoxy and radical on an alkene system. It does not prefer, right. So, we can eliminate that also. Then you are left with what? Ring expansion. That can happen. Can you think about taking the tertiary radical and putting on your oxygen? I am not, if I do that, I will not be generating oxocarbene. Can I generate? It is very hard. Can I do a decarbonylation? Why cannot I do a decarbonylation? See, it cannot stay like that at any circumstance. Okay, it has to do something. If I do decarbonylation, then think about radical. First, draw the structure, then you will know whether why this has to form now? That you have to ask yourself, because it is not so stable, right? Why it tries to form this molecule? Any idea why it tries to form? Yes. See, I can take this radical, okay, I can take this guy and use it. Yes or no? I can use that. So, if I use it, then I will end up what? See, type of ketone I am getting on. That is why it wants to push that direction.
So then I can cleave that A cleavage at alkoxy radical forming initial.
Which step? This step.
First step.
Here. So, what it drives you to cleave that? Here, see, I am getting a system like ketone.
Yeah. Where I'm flashing the light on the initial compound.
Yes. Yes.
They are also formed beta alkoxy radical.
You want to cleave this direction and get an alkoxy radical and acyl radical, but that time the tertiary butyl radical is more stable. The formation of that end radical will be more stable. See, that stability of radical matters. Okay. Now, I can combine this to give me this, I can get, right. So, if I do it in methanol, if I carry out, for example, if I carry out this photolysis in methanol, yeah, you will end up with a very nice product. See, now what happens once the double bond comes into the system, the chemistry is slightly changed. Your radical stability, that is why your radical chemistry plays a very important role. Okay. Once you get a radical, now because of that conjugation with that double bond, it tries to form that, otherwise it does not need to form that one, and gives you a ketone, then undergoes a cyclopropanation ring formation, then reacts with methanol. If it is there, you get the product. So, if it is a simple system, it is easy. So, and now we will take examples in such a way that we will make things little bit better understanding, for better understanding, rather than saying it tougher. We will take another example. I will give you assignments, okay, with some like carrying out 20 or 25 problems based on alpha cleavage. You can work out all these problems. Or otherwise we can have some class in which we can discuss also. So, now we have seen a butanone system with a double bond, right, to the beta gamma position. This is a cyclopentenone system, okay, with a double bond in the beta gamma. Now, we will see how this whole chemistry changes, okay, whether the formation of radicals, how they are trying to do. So, that is how it becomes like more interesting once you get into radical understanding these chemistries. Yeah, you can write many possibilities. See, what I suggest is that when you start working on photochemistry, try to write all your possibilities, okay, nothing wrong in it, write all your possibilities, then take the product, understand which will be formed most. It is even in exam I say that write all the products, nothing wrong. Yeah, you should not violate any rule. Without violating any rule, you write all the products, okay, then we can discuss. See, there are many products which will form. Once you go to the lab and do the condition, okay, then you know this is the major, then you go get back and try to substantiate that. But once you see the problem, if you can do like without violating any rule, writing the products is most welcome. Now we have a cyclopentanone system, fine. So what cyclopentanone system does, once I photolyze it goes to S1, okay. Then you have to write that it goes to triplet, it undergoes a inter-system crossing. So cyclopentanone, I carried my chemistry all from the singlet, okay. This then undergoes a your alpha cleavage. Yeah, since both are symmetrical, there is no problem in that, both sides are same. So, it should give me only one radical. I get this radical, right. This is your primary process. Now, we will see how it works in the secondary. That is where like little bit interesting stuff comes. What it can do now? It is a cyclopentanone. So, you have to think about cyclopentanone, what it does normally. What chemistry you see in cyclopentanone? One you see a recombination. I do not think like with this ring it can recombine. Another you see your intramolecular hydrogen abstraction. Since I have given methyl all over, there is no hydrogen for it to abstract. So, I completely get away from that. Then the final is your decarbonylation. So, that is how you have to see. Okay. So, then you get your decarbonylation. Right now, now you have to think what radical you are talking about. 1, 2, 3, 4. See, do that exercise slowly, like avoiding the process. Once you start avoiding, that means you are trying to recollect them. Okay. So, you have it is a 1,4 diradical system. So, 1,4 diradical system, what it does? What we studied 1,4 diradical system, they can recombine. Okay. Whether they recombine, yeah. If you have a cyclopentanone, you recombine to make a cyclobutane, right. So, recombination is allowed, that kind. You think whether this can recombine? No. Then what you studied? No, what you studied then? So, 1,4 diradical, what it does? What you studied in 1,4 diradical? Now only we studied beta cleavage. It is not possible in this case. I cannot cleave my beta then. Then did you study the hydrogen abstraction? It can't do hydrogen abstraction. So, yeah, we will come. Okay, we first see our formulation and see what happens. So, I can say that this radical can abstract an hydrogen from here, right. It can happen, because I will get then what product I will get? I will get I can get this, right. I can abstract an hydrogen from here because it is a methyl. So, I can get a system like this, but this product is a minor product, fine. So, I am not doing anything different, whatever formula I said, we are just using the same formula. But since there is a double bond involved, so I have to use this double bond somewhere. So, what happen? I can use them for making bond, right. I got a very nice product, but you cannot avoid this. You get this product also, Okay. That is why I said that you do with your formula, then you try to involve your double bond and see like whether you can work with your double bond. Clear? Hmm? There are n number of examples which we can work. We will work. I have a system now like this. Okay, what I will do is that I will write the product. Okay. Or you guys want to try it by yourself. I give you 2 minutes, 2 or 3 minutes. Can you try by yourself and tell me what is the product, or you want me to give the product and you will try the mechanism? You want me to give the major product, or you want to try by yourself? So, it is a cyclopentanone system. So, first thing you have to remember where you want to do an alpha cleavage. First do the primary photochemical process. You do by yourself. I will also try by in my paper. Okay, then we will see whether our product matches. System crossing to give me a check whether you got this product. Huh? Okay. Now, what it can do? It can do hydrogen abstraction, or how this product mostly look like. That if you have to little bit imagine. What will be the stable form of this writing this product? How, like, can you do any alteration there, so that you can get the anything you can, then you can think whatever you said is hydrogen abstraction can take place, but can you make a because you see the system has double bond, right. So, you have to somewhere involve the double bond. So, can I write the structure like this? Huh? Alright. So, I am just slowly involving the double bond there. I said you do not want a carbon with a radical with an OH, right. So, what I did is that just this carbon will be stable now. I can get this system now. Okay, you do not want that system to be there with a carbon with a radical with the OH. Now, what will happen? Now, I have a system like this. You want an abstract an hydrogen from where? Tell me from where you are going to abstract an hydrogen. So, from you have a choice here. You want abstract from here? No, from here. You want from here. You want abstract an hydrogen. So, that means you are not you are just seeing the molecule like that as I had drawn. Think about the molecule. It is like a cyclobutane with this thing. You want to abstract like this. If I just rotate this molecule like this, just because this is going to rotate, ne? It will be there, and then recombine, what will happen? Just taking this, okay, rotating up and then combining with that. See, these are tougher, I know these are hard examples, okay, but it is better that we do some hard examples in the class. See, the hydrogen abstraction taking from this hydrogen is not feasible, then you will be making an alkene system like this, which are like so, but that is what I said, na? It is a cyclobutane system, and you have to remember it is not like in the paper I have drawn, okay, it will be floating like this. You have a cyclobutane and it will be a linear molecule like this, right. So, it can always turn around, this can come down and make a cyclic system. So, we will take this type of examples and work. Okay. We will take one more another example. Okay. We will take a system like this. Okay, there is no double bond. Okay, so we are finished with the double bond, the system. So, I am taking a general example. So, whatever we talked about, like all the 3 examples we have seen: acyclic, saturated cyclic with a beta gamma unsaturated ketones. That is the 3 examples where you can see cleavage reaction happening in place, particularly alpha cleavage. It's clear. Okay, now we will take a general example. Okay. Now we will think about where this guy fits really, how we can do the chemistry, whether it is a 6 membered or it is a 5 membered, what radical I will get and what product I should think about. Using this all knowledge, can we solve this problem? Fine. So, we will do. So, you are thinking about what ring system. Since it is a ring system, you are now much more specified. Now, it is a ring system, and in the ring system there is no double bond. So, you can omit that. So, you have now ring system. So, ring system we have studied 5 membered, 4 membered and 6 membered. So, where this comes? So, where you want to put this? It is a 5 membered or 6 membered? So, is a so you want to consider this ring, like a 6-member ring. Think about like a 6-member ring system, right? Okay. Then think about it like a 6-member. So it goes to singlet, then triplet, fine, whatever it is, then undergoes a alpha cleavage. So first we will write that. So where you want to cleave your bond? Now alpha cleavage is there, so it's not a type of symmetry molecule. Okay, you have to decide. I can cleave this side or I can cleave this side. You have an option of cleaving that. It's clear that you want to cleave it A. So this is your primary process, fine, that's good. Now we will think about the secondary process and see whether we can do anything with that secondary process. Okay. So what you can think about from here? Decarbonylation. Okay, decarbonylation. If I do decarbonylation, for example, okay, we will do a decarbonylation as you said. I will do a decarbonylation. So what I am going to get up? So I will get see, that's why I said like it will be little bit from here. I get a radical. Why I want to generate? Why the molecule has to generate this radical? After this, what it wants to do? Yeah, you said decarbonization, so I try a decarbonization. I get an radical like that. Do you want to combine this radical? That's very hard. So that is not going to happen then. So
Proton will abstract that one. O dot, then it will recombine.
which proton will? No, no, I'm not getting it. So this radical?
No, that one, not that one, sir.
Okay,
Decarbonization.
okay. So decarbonization, you want to decarbonize this?
No, that radical beside O, that can abstract which.
Oh, we are another process. Okay, okay. Yeah, that's fine then. So first, decarbonization is not going to happen. No, we can cancel it. That's how it's nice that you work like that. Once you do like 4 or 5 problems, then you know by heart, okay, this will not go. Okay, but initially you have to work out. Okay. Then we can talk about like a sort of intramolecular hydrogen abstraction process. So we said that we can think about 2 products in intramolecular hydrogen abstraction, one acyl radical taking up an hydrogen or your alkyl radical taking an hydrogen. If I think about an acyl radical taking an hydrogen, so what I should get? This takes hydrogen from where? From where this can take an hydrogen? You said acyl radical can take, no? So tell me which hydrogen acyl radical want to take. See, it has to take means it has to take from here only. Then only you can generate an alkene. Do you think this is quite near for this guy to do this? No? For example, it does. Then I should get some product like I get a product like this. No, if it does, but do you think that it is possible for this to take an hydrogen? I don't think so. No? Okay, then we will try another thing. What is another intramolecular hydrogen abstraction we were talking about? Alkyl radical can take this hydrogen. Okay. So if that takes, what you end up? you end up with a ketene. See, something in organic like whenever we design molecules, you have to little bit understand, like say I have used this OH. Okay. See, if it is not participating much, most of the time you will never use it, nah? Right. So, since you have used this OH, you get an insight, yes, somewhere this guy is going to do something, not like almost true, but it is. So, you get a ketene now. So, what it can do? Ketene is not stable, it cannot stand like that, right. What ketene can do? Just think, I can take this and cyclize on your ketene. See, molecules are very clever. See, you get a very nice stable product. So, you have all these options, molecule had all these options, it takes only the easiest way, which gives it a stable product. Only we have to understand, okay. It takes always, it takes the right path, okay. We have to understand which it is taking. we did decarbonylation, then we thought it is not possible, then we removed it, then we thought about intramolecular hydrogen abstraction, we thought acyl can take, then we said distance is not a criteria, so we removed it, then we did ketene, and we know that there is a OH which can intramolecularly can attack the ketene to give me a 6-membered nice cyclic ring, right. So, we have many examples like this. So, since this is all about alpha cleavage reactions, okay. Other examples I can give it as an assignment, okay. You can work it out and then we can do corrections and everything. Next class we will start beta cleavage reactions, okay. Once we do beta cleavage, then the cleavage reaction is over, then we will go for an intramolecular hydrogen abstraction, okay. Clear. So, we will end up our class with this.